Well, this is going to be a lot of fun. The title for this webinar is Lighter, Stronger, Faster, the Future of Cylinder Bore Coatings. So we pretty much just spent a lot of time talking about the top end, and now we'll go just a little bit deeper. And Lake Speed Jr. joining us, and Charles Navarro, the president of LN Engineering. And Lake, first of all, tribologist is what it has for your title. So for those who don't know, elaborate.
Oh, for those who don't know, we should probably explain what the word tribology means. So tribology is a study of friction, wear, and lubrication. So as a guy that spent 15 years at Joe Gibbs Racing developing and testing oils, piston rings may seem weird, but the reality is the piston ring is a tribological device. It's not only a lubricated component, it's also the #1 source of friction in the engine. There's more friction between the cylinder wall and that piston ring rubbing together than any other component in the engine. So as a tribologist, someone that loves friction, wear, and lubrication, being here at Total Seal is the place to be. And that's why Charles and I are like peanut butter and jelly on this thing. He makes cylinders, we make piston rings. That's where the rubber meets the road. So should be a lot of fun today.
All right, that's perfect. And Charles, welcome, president of LN Engineering. So give us an overview of what you guys do over at LN Engineering.
We've been developing and manufacturing engine components for Porsche engines for the aftermarket for about 20 years now. And we're best known for our billet aluminum cylinders. And talking about cylinder technologies, we use Nickel plating for all our products. And some of you, if you're interested or are knowledgeable in Porsches, we also developed and patented quite a few of the fixes for the intermediate shaft issue that plagues a certain generation of Porsche Boxster Cayman 911 models. So we're also known for that.
Awesome. All right. Well, Lake, let's evolution of block materials, cylinder coatings, and all of that. What are we really going to be talking about here today?
Really, what we're talking about is just that. It's over time, racing has this great ability to elevate things. Things keep getting better. No different than, hey, 20 years ago, we had Nokia brick phones that could make a phone call and barely send a text if you knew how to push all the buttons the right way. Now you got more power than what went to the moon in our phones and can do all kinds of things. Well, engine technology has also elevated during that time. Just thinking back not long ago, Doug Yates was speaking at an event and it was talking about, 20 years ago, we still had qualifying motors in NASCAR. You had practice motors. An 043 3mm ring package was pretty state of the art at the time. Those engines would only live, one race, and they need to be rebuilt. And the reason for that is that, the power was down at the end of the race. So you built the fresh motor, not because it was broken, so that you could have the maximum performance. Well, 20 years later, we're talking about a 0.5mm or a 0.6mm, 2mm ring package. So it's half the size, yet those engines can run 3 times further with no performance drop off. Now, it was one of the things that the 2020 season taught a lot of those guys. They're like, wait, we can run these engines over and over and over again for longer and longer with less drop off and power. Why are we rebuilding these engines so often when they don't need to be? So again, that evolution of technology, where we were a brick phone 20 years ago, now we're an iPhone. That same thing has happened with every part of the engine. In the cylinder material, the block material, that interface between the ring and the cylinders also evolved. And that's what we're going to talk about today, is that piece of the evolutionary chain of how do you get that engine to go from one race only to now it can run 3 races and be better than it was 20 years ago. That's the topic today.
Yeah, and that's a pretty magical thing, especially when the mentality in a lot of places has been, as you even mentioned, like, at one time we had our qualifying engine and we had our practice engine, we had our race engine, and things were designed to do different things. And now in certain series, the rules require things to go much longer. And really the desire for a lot of racers is to have something that goes a lot longer. Charles, tell us a little bit more about you and just your history in this and, sort of what you've learned along the way.
Well, working with Porsche engines, obviously, go back decades, that the first all aluminum engine block would have been a Chevy Vega, and everybody knows how successful that was. But the general principle of having a hyper-eutectic engine block where you didn't have a iron liner in the bore, or you didn't have a coating like hard chrome or Nickel or something on the cylinder bore, that's used now by OEMs around the world. And the game with that is to maximize the efficiency, like the title of this webinar, Lighter, Faster, that they're trying to make the engines lighter, make more power out of them, and have them last longer. That's what we're all looking for. And with Alusil, the way that it works, and I'll circle back with why I'm talking about this in a second, but you have raw aluminum bores, and there's a special honing process that removes the aluminum and leaves silicon particles exposed. And then oil goes around those silicon particles. And that's what supports the piston and the ring on that cylinder bore, is that oil film with those silicon particles. And when those particles fracture and break down, at a certain point, you get aluminum to aluminum contact, because you have an iron coating on the piston that separates the aluminum from the aluminum. And when that all starts breaking down, we all know when you have similar materials rubbing on each other, they gall, there's added friction. And with a lot of the European engines that use Alusil cylinder blocks, Porsche's included, that we see cylinder scoring, and it can take out an engine with relatively low mileage. And at this point, the current fixes for that, putting a steel sleeve in it, which isn't the most optimal solution, using Nickel plating to repair it. And we'll talk about it later, but a lot of manufacturers are going into using Suma-Bore technology, or it's referred to PTWA. Ford is using it, Nissan's using it. A lot of the OEMs use those coatings, but a lot of the work that we do to repair aluminum blocks, we make aluminum sleeves, build aluminum sleeves, put Nickel on it. We've done it with Suma-Bore as well, but here's an example of a repair sleeve that we make out of aluminum, and you can kind of see that Nickel plated there. So that's a big chunk of our business. This year, we've probably done 100 Porsche engines this year with our aluminum Nickel sleeve repairs to address these issues with all aluminum engine blocks.
So Lake Speed Jr., where are we going with this? Where are we going with coatings and technology and all of that now?
It's like Charles was saying, the OE level is really similar to what racer mentality is, that we do want the vehicles to be lighter. The OEMs have a different reason than racers want. Every crew chief out there wants, if you're a circle track guy, you want light, low, and left. That's what you want. You want that car to be light so you can put the lead down on the left-hand side of the car as low as possible. That way you can adjust the weight balance of the car for optimal handling. So if I can take some weight out of the engine, I'm going to. Not only for whatever it does in terms of making the car lighter so it can accelerate faster, but more importantly for handling. So the weight's a big deal, which is why you're seeing OEMs go away from the big old giant V8 cast iron engines, and now we're getting into lighter 4-cylinder turbocharged engines that are aluminum block. Now, to Charles's point, when you go to that aluminum block, now you have to have something in that bore, because more than likely the piston's also going to be aluminum, and that's the rub. If it wasn't an aluminum piston, we wouldn't even be probably having this conversation necessarily. But because that piston's going to be aluminum, because of the advantages of aluminum as a piston alloy, now you don't want to have an aluminum piston against an aluminum cylinder. So now you have to put something in there. Obviously, the Alu seal, the localized silicon, was one way of trying to prevent putting in a sleeve, because now you got dissimilar materials and there's other issues there from expansion. When you get down to this Suma-Bore concept, like what Charles is talking about, that the OEs have adopted. I mean, Charles has got the list, and he can rattle them off for us real quick if you want to, Charles. Tell us all the OEs that are currently using Suma-Bore technology, and then I'll go to the whiteboard and I'll start drawing out what we're actually talking about so people can understand it a little bit.
Exactly. Volkswagen group uses Suma-Bore, so Audi, Porsche, Bugatti, Honda uses it, Aston Martin uses it, Cosworth, Yamaha, BRP with their Rotax engines, and Continental in aircraft engines, which Continental, going back decades, they've been using chrome cylinders, and chrome is not the optimal surface finish for a cylinder bore. Oil wants to run off of it. So what Porsche used chrome before Nickel was invented, and they actually put a spiral dimple. They went all the way down the bore, so the oil would get trapped in those little dimples in the chrome plating to help with lubricating the cylinder bore. And I've actually, Lake, have you seen that on any other chrome cylinder before, or was that something?
No, I've never seen that before. I thought that was pretty amazing. If you get that picture, try to show that picture.
Yeah, let me see if I can really quick. I'll share my screen. Let me see if it'll let me do it for a second so everyone can see it. Share. I think everyone can see that, right?
Oh, yeah.
Yeah, so you can see, obviously, it's an all aluminum cylinder, air cooled, and it's a hard chrome finish, and you can see those dimples in there. And the idea was to hold oil to help keep everything alive.
That's great. So let me, Brad, here for a second. I'm going to go to the whiteboard here, try to find my way around here and not crash everything. I'll see, sure people can see me here. Perfect. Okay. So the whole idea, while we're talking about oil retention and all this, is that I mentioned it previously. You know, the piston ring really has two purposes, right? It's there to seal the combustion chamber. And that's the obvious goal, right? If you had a piston sitting right here, make sure you can see it. So if we have our piston right here, and there's our connecting rod hanging out. The idea is we have the cylinder bore right here. We've got our piston. The idea of the piston ring is to be that seal in between, because the combustion is going to be happening up here. But that combustion gas we call it blow by, which is a term a lot of people heard, can blow by and get past the piston into the crankcase where your oil and all that kind of stuff is down there. Yeah, pretty much we're all familiar with the fact that we have to change motor oil in our cars way more often than we change transmission fluid or gear oil. Well, the reality is the base oil, not the additives, but the base oil in transmission fluid, gear oil, and engine oil is the same stuff. Now, the viscosity may be a little bit different, but chemically, it's all the same stuff. And the additives are a little bit different for each application, depending upon the type of contact and other little things I won't geek out about too much right now. I have to restrain myself, people who know me, about that. The key thing is that your transmission in your rear end, there is no combustion blow-by. Combustion blow-by is what kills your oil. What turns it dark, which makes you have to change the engine oil more often. So the idea of the piston ring is to do, again, it's got a couple of jobs. One is to seal the combustion gases so they don't get into the crankcase. Also, its job is to keep the oil, which is being flung up by all the motion down there, from getting into the combustion chamber. Because in the majority of engines, they don't want oil in the combustion chamber. You know, there's very few places where you want oil in the combustion chamber, because oil does not have as good an octane rating as gasoline does, or methanol. So you don't want that. So you want the oil down here, the combustion gas is up there, and then the piston ring is also conducting heat through the piston, through the ring, into the cylinder wall, so you can get the heat out of the engine. So thermal management is also part of the job. Okay, so with all that being said, back to those dimples. Why are those dimples in the cylinder bore? Why does that matter? Back to that piston ring isn't just, it's lubricated, where what's going to hold the oil to be able to lubricate the cylinder or lubricate the piston ring. It's those valleys. And I got a little tool here I'll show you real quick. There's a tool called the profilometer. This is our Mitutoyo SJ210. I'm going to turn this thing on. And now it's pretty bad because the screen's bright, so you may not be able to see it in great detail, but don't worry. That's why I came in Marie's office to use the whiteboard so I can do it. So there's these surface finish values called RPK, RVK, RK, and RA. RA is a term a lot of people have heard, roughness average. Well, RA will lie to you, so it's not even a good number to use. But we'll kind of, we'll talk about it a little bit, but just kind of know that RA will flat lie to you. So I want to do this page over here, and hopefully we can see it right here. The screen will there you go. It'll kind of gray out in a second, so it won't be as bright. Perfect. There you go. You can see it a lot better. That roughness on that screen, those peaks and valleys, that's the surface finish of the cylinder. And what we're going for here is those valleys, right? If we're talking about those peaks and the valleys. So the piston ring, we're going to imagine what it was looking like, right? Take that cylinder, turn it flat. So those valleys are what hold the oil. So the oil has two jobs when it comes to piston ring and cylinder wall contact. Number one, it's a lubricant. It's to keep the cylinder wall and the piston ring from wearing out. That makes sense, right? Oil is a lubricant. Number two, and just as important, oil is the gasket. No one in the right mind would put a cylinder head on a block and tighten it down without putting a gasket in there and think for a moment that it's not going to leak. It's going to seal up. There's all those surface imperfections. Someone has to fill in those voids, those imperfections. The oil is what fills in those imperfections on the cylinder wall. So it's the gasket between the ring and the cylinder wall that provides the ring seal. So that's why the surface finish is so important. Now, one of the things that Charles was talking about, and then Charles has got some numbers he can share with us because he knows this stuff really well, is that if we're looking at, say, that alusil, what can happen with those alusil is, okay, we got our aluminum substrate down here, okay? Then you got these little silicon nodules that are kind of popping up over here. So the piston ring, again, I'm going to draw it blown up, is moving over those silicon nodules. And it's the oil is kind of pooling in between those silicon nodules. So that's how it's working, is that alusil, any kind of that silicon-based thing, you got these silicon particles sticking up. Now, your traditional gray cast iron, iron liner situations, you're going to have this roughness where we got peaks and we've got valleys all along the way. Of course, the ring is bumping across those peaks, which we've probably all heard the term plateau honing, plateau finishing. Plateauing is all about coming in because the ring naturally plateaus while the engine's running. But part of the honing process, that plateauing is coming in and taking those peaks down. That way we don't have big giant peaks because the ring is what interacts with those peaks. But if we've got enough valley here to hold the oil, now we've got this big area. Of course, my Sharpie's not, my dry erase board marker's not working, so that's great. That valley can hold the oil to seal it up and to lubricate it. Now, Charles, give them a little bit of the rundown on what the differences in our RA, our roughness average numbers are for, say, an alusil block versus, say, traditional gray cast iron. And then we'll get into Suma-Bore because Suma-Bore is super interesting.
So with gray cast iron, typically just throwing out the average you'd see is 20 to 25 for an RA. And I just want to step back and just explain, because Lake did say that RA can lie to you. So let's say you have a bore that's honed and has very high peaks and no valleys, could have an RA of say 20, and you could have another bore that has no peaks and all valleys and could be the same 20, because it's a calculated, RA is a calculated number, and it could lie to you. So that's why you also have to look at the other figures, the RK, RPK, RVK. So looking at an Alusil bore, when you look at one of those bores, there's no visible crosshatch. You can't see any honing marks. It just looks like raw aluminum, gray, nothing you can see. And again, if those silicon particles you can't really see unless you have a microscope or a profilometer to do a trace on the bore. And those bores typically will have a very smooth finish, sometimes as low as say an RA of 3. But as they wear, bores will actually get rougher as they wear, because the silicon particles fracture, and then the ring drags those silicon particles across the raw aluminum bore, and that's what ends up eventually causing that scoring and the scratching of the bores. With Nikasil, that you obviously they're plateau honed, because unlike cast iron where the ring would knock those peaks off, Nikasil has to be diamond honed. It's so hard, if it's not honed properly, it's like taking a file to your piston rings. It'll wear a set of rings out in 50 miles. It'll just wear the rings out. So Nikasil has to be honed very carefully, and typically for an RA, we usually look at a RA no higher than 10. Usually when you get past 10, then you start either wearing the rings out or it just burn oil. So there's a happy medium. Neither is a good thing. There's very specific finishes. And going now to touch on Suma-Bore, that is a mirror finished cylinder. Again, just like Alusil, there's no visible crosshatch, no honing angle. And I'm going to show a picture of one really quickly. Let me share my screen. I got that one up here. So this is this is a Porsche M96 block. We took a Boxster 3.2 engine. We put our aluminum sleeves in it and increased the bore size to 101 millimeters. So that brought the engine from a 93 millimeter bore to a 101. And we put Suma-Bore on this block. It's actually in Lake's Boxster that he's driving around, and you can see that surface finish in the bore. That it is an absolute mirror. There's no crosshatch. I don't have pictures on this particular computer, but after our first round of driving the car, we pulled it apart. There was no visible change in the cylinder bores. They looked just like they were when it was put together.
We checked it with the profilometer, and there was really no movement at all in the surface finish values from brand new to even after 5,000 miles of driving later. So that was pretty unique, because typically you're going to see something, right? You're going to, even at a gray cast iron block with all those valleys that you can create with the normal honing process and crosshatch and all that, you would normally see those numbers decreasing over time, especially from at break-in. That's really what you're doing when we're talking about breaking in. People think about breaking in rings. Really, with today's ring technology, you don't break in the ring. You're breaking in the cylinder wall. The idea of ring break-in goes back to the old days when we had chrome-faced rings. Now, the rings were actually iron. They weren't chrome, but they were chrome-coated. And that chrome plating process actually is a chemical dip process. It's not like super consistent in terms of thickness. So the ring could be 100% light tight, perfectly round in its natural state. But once you chrome it, there's going to be these waves, if you will, around it. Of course, it's hard. So in the old days, people put in non-detergent oils and things like that, and they had to break in the engine for thousands and thousands of miles. And the whole idea was you were wearing that hard chrome, wearing those irregularities in so that it would then seal up. So it would then be perfectly round, fit in the bore. So you also would have really rough cylinder finishes, very high core roughness, very high peaks to wear in that chrome so you break in the ring. Well, with today's steel ring technologies and thin PVD coatings, you're not breaking in that ring. Rings leave here, we check them in mercury gauges, and they're light tight. They're perfectly round before they leave. You put it in the cylinder bore, which breaking in is that cylinder bore. To that, there's a little bit of mating between the two processes, but pretty much it's the cylinder bore that's breaking in. So, Charles has given you some of those numbers. Say a Nicosil is going to be somewhere around 7 to 10. Alusil, Charles, what, around like 5?
It charts out smoother and it gets rougher as it wears in, and then with the Suma-Bore, it usually comes in the 5 to 7 range, somewhere in that neighborhood. But again, that it's a good example where RA can lie to you, because there's no crosshatch, there's no honing marks. You can't even tell that the cylinders have been honed, but yet it's still has a mirror finish, yet it has a roughness average that you can quantify. And that's because the Suma-Bore coating, once you hone it, there's micro pores. You can't see them. You have to use a microscope to zoom in on there. But those micro pores are what hold that oil and provide the lubricity. And what's really neat with the Suma-Bore coating is that it's a powder. And basically the powder gets superheated and gets sprayed onto the bore. So as it's being sprayed, it melts the aluminum and it permanently binds to the cylinder bore. And they can also tailor the actual powders that are used for the Suma-Bore depending on the application. In our test engine, we used their 2071 coating, which is used by MAN in Europe for all their diesel engines. So all the diesel engines, really high compression turbo, high sulfur, they're exposed to sulfur fuels, probably the hardest conditions, and those engines have to last millions of miles. So we chose that coating for our test engine, and it uses zirconia ceramic mixed in the powder, so that provides a very, very hard, durable surface.
It was like Charles was saying, it was really cool because that powder, and when you look at it with the profilometer, where you would normally have all this crazy roughness or these peaks and all these things we talked about, with the Suma-Bore, because again, it's a sprayed coating. And a good way of kind of thinking about it is this, that let's say we had a bunch of, because there's that powder, right? It's little balls, little pellets, if you will, of iron being sprayed onto the bore. If you think about, say, a barrel full of golf balls, if you put all these golf balls together, especially if they're kind of, some variance in sizing, you put all these golf balls together, and then you come along and you hone it perfectly smooth. What's going to happen is you're going to have a completely flat top, no peaks. Then you're going to have all these voids in between. That porosity is what holds the oil. That's what makes Suma-Bore from a tribology perspective, it's like the perfect cylinder bore material. It's finished because it's mirror smooth, perfectly flat on top. So it's got a great load bearing area, tons of load bearing area. And it has all of these pores. And then really, I'm drawing valleys here because that's what you see on the profilometer, but it's really not valleys. It's these pores that hold the oil. That way you've got basically like a sponge, if you will. That cylinder bore is a sponge holding the oil to lubricate the ring and then to seal. So it really is, from a tribology perspective, a perfect cylinder bore material or finish in it necessarily. So that's what's kind of cool about it, is that it has all those pores, it can hold that oil. And then the other thing about it, like Charles was saying, it's extremely hard. If you go back to our gray cast iron, the hardness of those blocks is, they're not anywhere near the 450 Vickers hardness that Suma-Bore is. So where with Nikasil and Alusil, very smooth, but you've got these vertical orientations. That's your challenge, is that you've got such a fine line you're trying to dance there from the tribology perspective to lubricate and to seal. And it's hard, but it's delicate. Over here on the gray cast iron side, it's softer, it's easier, more forgiving, but it wears out faster and it's heavier. So that's what the beauty of Suma-Bore is that you're spraying it in to that aluminum cylinder so it can be there. So you have the similar materials. It has that porosity so it can hold the oil and be that sponge. It's mirror smooth, so it seals perfectly, carries the load. And if you're thinking about what I'm talking about in terms of that load carrying ability, think about this. If you ever tried to do push-ups on your fingertips, you know that your fingertips, and it's going to hurt really bad, and you're not going to want to do a whole bunch of them. So it's going to fatigue pretty quickly. If you do them on your palms, you can do more. So a surface that's got a lot of peaks is like trying to do push-ups on your fingertips versus doing them on your palms where you have a larger area to support that load. So that's kind of the advantage when you're thinking about it from a friction and wear reduction. That's what it can do. So again, that's what one of the advantages of taking an aluminum block, spraying it with Suma-Bore as opposed to putting a sleeve in it or plating it with something like Nikasil. That's an advantage. Now, the other thing we haven't talked about yet is that Suma-Bore also has, because of what Charles was mentioning in terms of that longevity, how long that cylinder finish lasts. Now, let's say you have a gray cast iron block. Let's say it's a race block that's got lots of prep done to it. And now you're at the last oversize because maybe there's rules in your series that say you can't run a bore diameter larger than X. I think I know of a series that does that, or this from a block material perspective, you can only take so much out before now it's too thin and you're going to cause problems. Now with Suma-Bore, that block can be saved. You can spray it in, create that, make it smaller by spraying it in and be able to save that block. So from the pure race perspective, the friction wear, lubrication perspective is a benefit. From a historic restoration perspective, now there's a way to save that original stock engine that has the matching numbers and all the things that makes that car, makes that engine valuable. Now you don't have to worry about that engine wearing out. You can save and preserve that engine by employing this technology. So that's what's really cool. And Brad, you and I talked about it a little bit yesterday. This isn't new technology. This technology has history already in NASCAR, Formula One, Indy. It's not new. I know from Charles and I have talked to the guys at Oerlikon Metco that make Suma-Bore. They've used it in a lot of industrial things like over in Europe for a long time. It's been at that OE level, obviously, for several years now. What we're talking about is there's some things in the pipeline right now. They're going to make this technology available for the general aftermarket racer enthusiast in the next couple of years. So that's why it's like, hey, this isn't just super uber technology that is crazy expensive that no one can ever employ at a grassroots racer level. Now it is something that will be accessible before too long. So it's now the time to start kind of thinking about, okay, what is this technology? How does it work? How can I apply it to my program to get the best benefits for my program? Because again, we're all racers. In lighter, faster, stronger. That's what you're trying to get. And the Suma-Bore can actually deliver on that.
So how does this change the way I think then about my engine in that, is it going to change, either the piston or ring selection that I'm going to be using? Is it going to be changing the oil that I might be using? Does it give me more options for any of those things?
It's going to change all of those things is what it's going to do. And that's one of the reasons why Charles, myself, and another guy, Jake Raby, if Jake's watching, hey, Jake, a good friend of ours, we've all been working together. I mean, Jake is the man thrashed. He's got a 4-cylinder air-cooled Porsche engine on his dyno. He's down in Cleveland, Georgia. And from Christmas Eve through almost, I think about Valentine's Day, he ran 15 different dyno tests during that month and a half on a Suma-Bore engine. Now, the trick is, because it's an air-cooled engine and it's a flat engine, we started off 1/2 Nikasil, 1/2 Suma-Bore, and put in the same ring package, the same oil, the same everything we would normally do for Nikasil to see how it would do with Suma-Bore. And we learned in the very first test, it has a completely different appetite than Nikasil. So it's like, okay, forget everything we thought you knew. It doesn't apply anymore. Take the Nikasil cylinders off, put in Suma-Bore cylinders, and let it start changing. So, back to talking to Matt and Keith and the guys here at Total Seal, it's like, okay, we've got experience. We need to change this type of ring coating. We got to change this type of ring tension. Use my tribology oil experience. We need to change this type of chemistry. So we changed everything of all the stuff you mentioned in about a month and a half. And the cool thing is, what really brought about we'll call it the impetus to do that air-cooled test and to focus on it as hard as we did really was because the very first engine we put together with Suma-Bore is the M96 water-cooled engine that Charles showed that's in my Boxster right now. Because 5,000 miles later, it was not going well. It was not doing what we had hoped it would do, following the same regime that we knew that would work with Nikasil. So it's like, okay, we put together the engine and following the Nikasil package, it didn't work. So we knew we had to kind of start over from scratch. And that's what really brought about Jake's involvement. Say, we're going to start half and half. Let's evolve. Let's come up with something. We found a package, thanks to Jake's hard work and everyone's effort to thrash, change. Tons of oil analysis. I don't know. We have a spreadsheet probably this long with all the profilometer readings after every single test to see what was going on. Now we got it. We put together the engine back together, different oil, different ring package, everything, boom, sealed right up, dried up perfectly, running great. So that's what's kind of been neat to see, that we've done in about 9 months the amount of work in R&D that would normally take years, thanks to Jake and Charles and everybody's efforts to kind of tag team this. So I feel like we're really on a good point now. Now we want to move into turbocharged engines and get into out of a few different applications, try some different fuels and throw some things at it to see what the limits are. Because again, back to the tribology, friction, wear, lubrication, as you change those variables, like you alluded to, Brad, you're going to have to change that recipe. Because ring seal, and if Keith Jones is out there watching, he knows exactly what I'm about to say. Ring seal is soup. It's not steak. Now, if you go to dinner tonight and you order a steak dinner, they're probably going to bring you a steak and a mashed potato and maybe some broccoli. Well, they're all on the same plate, but they were all cooked individually, and one can be great and another one can be terrible, and you can still eat one of them. That's not what ring seal is. It's not about, oh, the ring's great, the cylinder wall is fine, so it's going to work just fine. No, they all have to work together. The ring, the oil, the cylinder, the piston, it's soup, and they're all interdependent, which is why I love ring seals, why I love engines anyway, because they're all independent, or not, they're interdependent, not independent. That's what makes it fun, is because there's all these variables and you got to dig and dig and dig to find them. And that's what, Charles and Jake and myself, we've all been working together on this program. And the Suma-Bore really does bring in some interesting variables to the equation. So I really see, as we go forward, there will probably be a different soup for each of the different iterations and applications of Suma-Bore based on what that application is. Say, for example, going from a NA gasoline fueled setup to a turbocharged or supercharged methanol E85 setup, there's going to be some variances there, just because you're throwing so much more fuel at it. So you're going to be trying to wash it down. So, the viscosity of the oil may just be what fixes it, or it could be something to do with the ring coating or the ring thickness. That's our job to figure that out. And then we'll have another webinar and say, hey, here's what we learned. You got to do this with that, and you don't do that. And because what we mostly learn is by our mistakes. If we're all being honest with ourselves, we all thought we had an idea what we should do, and it worked out that was the right thing to do. And it's all about recognizing those red flags and then responding to them. Engines cannot be rationalized with. You cannot tell it, hey, well, this is what the book said. It doesn't care what the book said. It's going to do what it wants to do. You got to listen to it and then figure out how to be that engine whisperer. What's wrong? Tell me. I got to listen. And now we're going to adjust and work from there.
Well, we had a question on the chat from Mike. Says, I have an engine that needs this now. How do I get it today? How soon?
Sorry, unobtainium. We're being the big giant tease here. I know Charles was sending some emails this morning to the guys up there at Oerlikon, and some of the R&D stuff. We're like, yeah, you still can't. We want it right now. We still can't get it right now. The simple fact is, it takes time to build the process. And we talked about it a little bit, but this is a sprayed coating. So the fixturing that you have to understand, if you think about how you would spray a cylinder, the cylinder's within an object. They have to be able to have the device go in and then turn at the correct radius, the correct distance from the cylinder to apply it evenly. They've got to know the bore and the length of it, so what that feed rate is. So there's quite a bit of engineering on their side to set up to be able to coat the cylinders, not just like, just grab a spray gun, or here, put a ground strap on it and dip it in a tank and call it good. It's not that simple. There's a little bit more prep work on the front end. So, but hopefully, again, that's what we're doing this for, is trying to help figure this out to bring it to market.
Yeah, and and there's one reason we did it with an M96 and with an air-cooled Porsche engine. It's really simple if you have eventually, this is a lot easier to have to coat than a small block Chevy engine and fixturing. This is pretty damn easy to fixture up. So we started with something really easy, and obviously engines that we're very familiar with, that we've been doing for all these years, and we know ins and outs, how to do them perfectly with Nicosil. Like we said, that's what we started with, because Oerlikon really had no guidance to tell us, because they sold the process to the OEMs. They don't do the coating for the OEMs. They sell the equipment and powders to OEMs. Well, the OEMs don't say, here's what rings we use, here's how we hone the cylinders. They keep that to themselves. They don't want to share that information. So even Oerlikon doesn't have that information. So it's up to us to figure that out. And that's why it's not quite ready for
prime time.
Yeah.
So how, when it does become ready, I mean, what are the obstacles? I mean, obviously you talked about just the process and being able to do it, but Lake, you also talked about, maybe still some trial and error going on, when this truly is going to be ready for people to get it. And when they get it, they're going to want to have it right. What kind of a timeline do you think we're looking at?
I really think from a ring material and coating and lubrication perspective, I really believe we've made tremendous strides in the last 9 months. I think in the next 9 months, we'll be able to verify all of that, and we should be able to throw enough variables at it and have that under our belt and feel really confident. That's one of the great things about having a car on the road running these things in real world conditions, that we're monitoring ourselves. I know what I did to the car, right? I know what fuel I used. I know what oil I changed, and when I changed it. We've got oil analysis. We'll have a good handle on those variables, I believe, by the end of this year. the next hurdle really is more to kind of to Mike's question. Again, I'm sorry, Mike, that we're teasing you that way. Is it's about, okay, it's the fixturing, the setup. If you're, when you're taking a brand new block that's never been used, that's going through production, it's clean, it's been QC tested, it's a known entity. You can go and you can spray it, you can hone it, you can do all those things. On a production basis, that's a really different story than taking existing engines, existing blocks that are dirty, that need to be checked to make sure they should be even had this done to them, and then cleaning them up, and then creating the fixturing to get them done, and then the torque plates to hone them, and all that. It's what I see this coming out as, is that this is a technology that will probably be best in new blocks, new sleeves that are available in the aftermarket. I'm sure there's going to be some people that have restoration pieces that are willing to take the time and spend the money because of the value of the car, right? If you've got a 1926 Bugatti Grand Prix car that's on this last oversize, what it costs to do this and the time it takes is irrelevant to the value of that car. So for those situations, put those exceptions aside, I think for the majority of it, it's going to be new production, kind of like what Charles is doing with their company, new production going forward. That's the easier path to tackle.
So if I'm ready for a rebuild right now, I can wait a season or so, before this is right. If I'm looking at a new build, but I really want this, I'm just going to simply have to hold off and be patient. That fair?
Yeah, I think this technology probably, I think it's going to be available within a year to 2 years. And it's a big window. I understand that, but the world is crazy right now. It's hard to predict what's going to happen next week. I think if anything, the last 12 months it told us, don't plan too far ahead. You'll make a fool of yourself. I do think that we're probably within the next couple of years, this technology that can come to the market and start to be out there again at the new manufacturing level, probably first, and then moving itself gradually out into the, hey, I can send in a block, and then it can be reconditioned and honed. And because one cool thing you mentioned earlier about how you order rings and order pistons is that with this, what we've seen, it's not wearing, you're not going to oversizes. So if you set your engine up as a 4.0 30-inch bore, that's what you're going to have. You're not going to have to get oversized pistons. You're not going to have to get oversized rings. You're going to order the same thing over and over and over again. And you're just going to keep on running for a long, long time because it's not going to wear out and it's not going to be oversized. And there's a huge advantage right there, because a lot of times, now look at the complexity of all the stuff we have here, from a 4-inch bore to a 5-inch bore engine, just that range. We have ring sets at every 5 thousandths oversized interval. That's ridiculous. But people do that because people are going to have a 405, 410, 415, or 420. By one at file fit, so it's 425. So it's there could be some great simplifications, which could be a big help, because that's what happens. I mean, I see every day people are looking for parts, and to try to find the part that's the right size, sometimes that can be a challenge. So hopefully this will be something that can help with that.
Charles, you want to add?
Yeah, and as far as, because this is kind of a tease, as Mike mentioned, that in short term, and obviously Nickel plating has been around for decades. I anticipate it will still be around. We're going to continue using it. It works really well. The Suma-Bore may be a different price point. Right now, it's definitely many times more expensive than Nickel. Hopefully, once it becomes more mainstream, that cost will come down a bit. But for someone that's looking to repair something, that is irreplaceable, or they're looking for a performance gain over, say, a iron sleeve and aluminum block, or you can even put Nicosil on iron blocks and iron bores. That process is a proven process that is available. And Nicosil, like Suma-Bore, being that it's very, very thin, both the Nicosil plating and the Suma-Bore coating is only put on the bore 4 to 5 thousandths thick. So it's not a barrier to thermal transfer. So that's one of the reasons manufacturers went to all aluminum engines and now are looking at the Suma-Bore is they're increasing compression ratios. They're putting more boost through the engine. They're making more horsepower per cubic inch of displacement. So the engines are making more heat, and the heat is transferred from the piston through the ring, through the cylinder wall. And if you can't cool the piston and ring assembly, you can't do everything else that you need to do to the engine to make that power. And going back, a good example of taking an iron block engine and going to an all aluminum was the Toyota 2ZZ-GE engine that was used in the Lotus Elise. That engine started with an iron block and then went to an all aluminum block. And changing nothing but going to all aluminum, they were able to get, let me look real quick, 25% more horsepower and 5% more torque with no increase in displacement by ditching the iron bores out of the engine. So those are just some of the gains that you get going to a technology, whether it's a Nicosil plated bore or a Suma-Bore coated bore, where manufacturers can take an existing block and they can decrease the distance between the cylinders. So normally a steel sleeve has to be fairly thick in a block. Well, if you can ditch the steel sleeve, you can put a bigger bore in the engine and get more displacement out of an engine without actually physically having to make the engine a larger footprint.
Wow.
So that's one of the reasons the OEMs have pushed that way.
It sounds like amazing technology. By the way, Mike Norman was thinking along the same lines as me. He says his application is a V-twin racing motorcycle, very similar to your Porsche. Can he be a tester? I've got a BMW Boxer that I ride around the country. I'd be happy to volunteer as well.
Yeah.
But this really does sound incredible, and obviously something on the horizon that, look, anyone who uses anything with an engine, it sounds like, automotively, but especially in a racing application, who wants something new, wants something that can really improve not only their performance, but their longevity. It just sounds like a huge game changer.
Yep.
It is. I mean, it's when you look at, Mercedes and BMW and, like I said, VW, Audi, Porsche Group, when those kind of OEMs make that kind of investment and they change and go to it across the board, that speaks volumes. It's that this kind of technology is what is enabling higher levels of efficiency, and it is trickle down. Obviously, as I mentioned before, this is technology that's been employed at the highest levels of motorsports for some time. So it's not super new, but the OEMs learn from that and they say, listen, this stuff really does have some really great benefits. We want to apply that to production car environment because we see the benefits of it. So to make that door open to take that technology and bring it to the aftermarket is actually super exciting. It's been neat. Total Seal's been working with Oerlikon Metco for several years on this technology, back from our supply side to the high-end race teams where we first were introduced to it. So it's kind of cool for me, being a Total Seal guy, to see this progression over time. It's like a lot of things. Early adoptions, it's hard. It's like, what is that? That's weird. And then all of a sudden, you see it really interest starting to take off, and obviously putting it at the OE level and having hundreds of thousands of engines built each year using the technology, that just greatly expands the knowledge base of this product. So again, I think the future is really bright for this technology, and we're excited to be able to be a part of it. And thanks to everybody at EPARTRADE for giving us a chance to come and talk about it and share it with the industry, because this is a great platform to be able to do it, that we can do it here in the middle of toward the end of March and not have to wait till December to talk about it.
Yeah, this is great. Before we close this up, Lake Speed Jr. or Charles Navarro, first, Lake, do you want to say anything else about Total Seal Piston Rings? I mean, there are people who are looking to do things today as well with the current today technology. So how can you guys help them?
Oh, thank you. So obviously, being here at Total Seal, if you're working on something, we've got a lot of really neat new technologies. One of the last things we've come up with in the last couple of years are the gas-ported piston rings, where we're putting the lateral gas port in the ring as opposed to the piston. In fact, the engine that's in the car, right, the Suma-Bore engine in the Boxer happens to have gas-ported top rings in it, because that was the thing we saw on the dyno testing that made it seal up better. Because piston rings are not sealing by the tension of the ring. It's not the top ring tension that causes the seal. It's the gas pressure getting behind the ring and forcing it out. So the gas-ported ring is just the next evolution, just kind of like Suma-Bore is the next evolution of cylinder bore technology. The gas-ported ring is the next evolution in piston ring technology. So if you want to learn more about that, you can pick up the phone, give us a call, 623-587-7400, or go to totalseal.com. We've got lots of stuff there. Unfortunately, there's a lot of videos from this kind of high energy guy that wears glasses. If you can get past that guy, there's some good information there.
We like that. And Charles, how about you? LN Engineering, if someone needs some of your help, what are you guys working on? What can you help them with?
We specialize in repairing Alucil Locasil engine blocks. Again, with our aluminum Nickel sleeve processes, we also manufacture air-cooled cylinders. Someone asked, what do? We do air-cooled Porsche, Volkswagen, and we also do Rotax cylinders. A lot of those go into light aircraft. We do quite a few of those a year. And we do a lot of custom stuff. We have a full machine shop. We do everything in-house. The only thing that we don't do is the plating process, because that's very restricted in the EPA. That's one of the reasons OEMs have gone away from using Nickel. It wasn't because it didn't work. It's just that, especially in Germany, that they're trying to do everything green, and the Suma-Bore coating process is inherently an environmentally friendly process. There's no chemicals, acids, etc., that you have with a Nickel or any kind of plating process. So,
wow, that's pretty incredible. That's like a win-win all the way around. Well, the title of this was Lighter, Stronger, Faster: The Future of Cylinder Bore Coatings, and we look forward to when we can talk about the present when this future actually gets to us. So, Lake Speed Jr., Charles Navarro, thank you both so much. I mean, really just a great informative webinar here today.
Thank you, Brad. Appreciate the opportunity.
Yeah, thank you, Brad.
Here's Judy and Francine. How y'all doing?
Hello.
Thank you, guys. Thank you. That
Very
was
educational. Thank you.
absolutely what a great sessions today. First with Ferreira and now with Lake and Charles. So thank you very much for joining us today. We will be back next week. Next week, we'll be talking brakes with the great people from Pagid Racing. And so we're going to have a single session next week for an hour on racing brakes. This session has been recorded as well as the one earlier today. They will be posted on the EPARTRADE platform later today. Thank you for watching us. And as Lake mentioned, his products are on the EPARTRADE platform right now, as well as Ferra, as well as Earlycon. We push them as well back to the top. And we have a long story also with Earlycon. So thank you, Charles, for joining us for the second time. You still are 2 slots behind Lake, who is number 1 with 4 participating. But no, thank you very much. It was a great session. Brad, thank you so much for hosting both webinars today. It was a lot. So you can now take a little break. We'll see you guys next week. Judy, you want to end this?
Just thank you, everybody, for attending this. And we can't get better than having Zeke and you on Lake. So thank you. And Luke, and of course you, Charles. So
Thank you.
Thank you, guys. We'll see you next week. Bye.
Bye.